Hi, good morning. It seems like recording have start, so I guess that is an indicator for us to start. So let's start the session. Welcome everyone to this session of Variability and Product Lines number 2. And we have one journal first paper and 5 technical papers in this session. And each our presentation will have 5 minutes in order. The presentation will happen in the order according to the programs, not in marketplace. So for the presenter, please get yourself ready according to the order. And our first paper is journal first paper, transferring learning across variant and versions, the case of Linux kernel size. And I have seen, or did Jamal have just joined us? So did Jamal please go ahead, share your screen and you can start. Hi, I can, yeah, okay, yeah.
Can you hear me now? Hello? Hello, hello. Can you hear me?
Yes.
Okay, perfect.
Yeah, you can share
Sharing
screen, yeah.
slides. Or I thought I'm gonna be second in order of presentation. I thought so. Oh, sorry. So how can I share?
At the bottom, there is
Okay.
like a screen icon.
Okay. Okay. Yeah.
There's a screen icon, yeah.
Yes. Okay. Okay. So that's perfect. Okay, just one thing. Sorry.
So for other attendees, feel free to put your question in the chat while the presenter is doing the presentation. And please have the presenter name and then your question so that when we go through your question, we know like who it is for.
Okay. Do you see the
Yep.
screen? Okay, good.
Yeah, we can see the
Perfect.
screen. Go ahead.
Yeah, sorry for the delay again. Okay, so yeah, sorry again. I'm Jamaldin Kaladi. I'm going to present actually on behalf of Mathieu Haché at the last minute. Sorry for this. So our paper, transfer learning across variants and versions in the specific case of Linux kernel size. So basically the context in which this work occurs between, so we want to aim to tackle huge configuration spaces, and for this we chose the case of Linux kernel, and in the case also to build prediction models for various purposes. So we want to address the variability in space. For example, given different configurations, how can we predict some performance indicators, such as the size. In this example, you see on one side we can have 7 megabyte of size and another size for another configuration. So and once we build this, and we put so much effort in building this prediction model for a given version, well, we face the other variability dimension, which is variability in time. And in the case of Linux, again, it evolves a lot, actually, very frequently. So we have, I think, weekly to monthly releases, and they are very active. And we can also see this in this figure that I'm showing here, where we can see that the number of features actually over 3 years period evolved from 10,000, 11,000 of features up to 15,000 of features. So there is a need of answering whether we can reuse this prediction model we use, and if we cannot, can we apply some heterogeneous transfer learning to reuse it on later versions? So we started by first answering this question: can we reuse a prediction model that we among versions? So to do this, what we did, we selected several versions of Linux kernel, starting from 4.13 to 5.8. And basically, we built a prediction model for the first version, and then we simply wanted to reuse it across other versions. And we see here in this figure that actually the error or the accuracy or the error rate increased from 6% up directly to the next version. We tried to 20% and kept increasing roughly to 35% of error. So we clearly see that there's a degradation, and we cannot simply reuse the prediction model. And here we have a period of 3 years between the different versions. So basically what we did in this paper is we wanted to propose a heterogeneous transfer learning basically on the feature. So because the feature space is so much different, there's a lot of features, thousands that are added, removed. So we had to apply this heterogeneous transfer learning, and we proposed an approach for transfer evolution aware model shifting. So basically how it works is given, or we build software prediction model for source version. So in our case, let's say it's 4.13. And the goal is to transfer it to another version. So what we do first is we try to align the feature space. What are the features in common, added, removed in each of the two target and the source. And then we train additional data, additional model on the target version. And then we try to also reuse the predicted values we already have in the source model. And one thing we observed that I'm going to show also in the results is applying a simple linear model shifting is not sufficient. I'm going to show it in the next slide. So also as a bonus in our team, in our approach, is we are not only able to shift to transfer the learned model from one version to another, but we can also do incremental steps of like compositional transfer. So in the evaluation, the main results, we evaluated teams on three budget for shifting. So we used for the targets prediction model 100 configuration, 5,000 configuration, and 10,000 configuration. And overall, we see that the model shifting basically is always beating if we have built a prediction model from scratch with this budget. And of course, the more we increase the budget, the more accurate we get in the case of 10,000. And two other points before I stop. So here we see on the top with the green line shifting. So linear shifting does not work at all. And also, maybe you don't see it, but at the first line, we apply two kinds of model shifting from, let's say, the one source, fixed source model to different versions. So from 4 to 5, from 4 to 5.set. But we also applied incremental model shifting from each version to the next. And we clearly see no main difference in results. So both works really, really good. So yeah, that's it for me. The paper is available in preprint in this link, and I would welcome any questions. Thank you very much.
Well, thank you very much for the sharing. Okay. Yeah. And so the next presenter we have will be so the next paper we have our SAC presenting the paper Zugacy, Scalable Desugaring of Real-World Preprocessor Using into POC. Okay, we
That's a
want
long
to
name.
yeah, want to welcome Zach for that.
You want me to just get started?
Yep, please go ahead.
Okay, sure. Okay, so I'm Zach Patterson, and I'm presenting Sugar-C, Scalable Desugaring of Real-World Preprocessor Usage into Pure C. And this was done alongside Zeno Zhang and my advisor, Dr. Wei, at UT Dallas. And we collaborated with Brent Pappas and Dr. Gazillo at University of Central Florida. So software product lines make very heavy use of the C preprocessor. However, it's an issue because most static analysis is variability oblivious, meaning it only runs on one configuration at a time. So if we look here on the right, you can see that we're assigning 256 to a character, but the limit is 255. So we might be introducing a bug here. But we only see this if we compile the code under the condition char. And so the idea of variability aware analysis is really appealing. But instead of trying to create some kind of new analysis to look at all of the data and data structures that you would have to make, we want to try and change the representation of the preprocessor. And so the idea is to convert the C code and the preprocessor code together into just pure C, or to de-sugar it. And this is something that we can try and more easily adapt an existing tool to, rather than making a new one. So a few tools have done this in the past, Hercules and C Reconfigurator. However, they were only applied with informal models for their transformation rules, which led to a limited support for actual C features. Sugar C, on the other hand, in our contributions are that we implemented a new syntax-directed translation approach, which is specified on the formal C grammar, which means the C constructs for which we support are very explicit and well-defined. We also added some novel optimizations to make it actually work with real-world code, and we added a new micro benchmark, dsugar bench, which focuses on C language features. And to evaluate it, we compared feature support to the past tools, and we tried to desugar real-world code to show its scalability. So we consider the preprocessor to be syntactic sugar, and so to desugar it is to remove the preprocessor while still maintaining the same semantic equivalence. And we do this through a series of duplication, renaming, and implementing type error functions. So you can see here on the right, we've got unsigned int x associated with x1, and the accessing of x1 is wrapped inside of an if statement, which is associated with the presence condition or the configuration space. X2, same, being char, and then in the case where we have multiple definitions of x or no definitions of x, we are referencing a type error instead. So for optimizations, we combined all of our struct fields together, which led to interesting solutions for size of flexible arrays and struct initializations, as well as we did some interesting things with struct forward references. There's more details on all of this in the paper, which I encourage you to go read. And for the evaluation, we asked two main research questions. Does Sugar C support more language features than existing desugars, and can we desugar real-world C programs? So dsugar bench is 108 C files, all with configurations split into 12 language feature categories. Once again, we made this micro benchmark for the study. And our primary metric is, do we have the same semantic equivalence in our output as we do on the base file? And we ran this on Hercules, C Reconfigurator, and Sugar C. And this table has our results. You can see a green cell means that it was a fully supported feature. Orange means partial, and red means it wasn't supported at all. The values on the left are the number that are correct or semantically equal, and the one on the right either did not work or had some issue. In the right hand, on the gold total column, we can see Sugar C supported 97 files versus the other work only supported 32 and 73 respectively. So yes, Sugar C does support more features than Hercules or C Reconfigurator. To run on real-world code, we ran on AXTLS, Toybox, and BusyBox, which we chose for their use in configuration research, as well as their large number of configuration options and moderate size of files. And our metric is, can Sugar C process this and produce an executable output in 1 hour? And the answer is overwhelmingly yes. We supported every file in AXTLS and Toybox, as well as 516 of the 565 in BusyBox. So in conclusion, Sugar C uses a new syntax-directed translation approach, which leads to more sound support for structures. We did type checking and parsing simultaneously, and we optimized for real-world code. We outperformed previous work, and we show that we are scalable to real-world code. In the future, we're going to be working on linking for full program desugaring, continuing our feature support, and translating and creating a framework to translate variability, oblivious tools for variability-aware analysis. Thank you. You're muted.
Thank you. Thank you, Shek, for sharing. And then our next presenter will be Aaron, and he is sharing with us on his paper on the benefits and limits of incremental build of software configuration and exploratory study. So Aaron, please go ahead.
Thank you. So hi, my name is Aaron. I'm a PhD student at the University of Rennes. Today I'm going to present you our paper on the benefits and limits of incremental build of software configurations and exploratory study. This is a joint work with my colleague Javahiri and my PhD advisors Jamel and Mathieu. So in this paper, we are considering highly configurable systems that are configurable through the compile time options. And here we have 3 boxes with 1 configuration each, which are compile time options from the same software system, configurable system, which is Xterm, terminal emulator. And to test these configurations or to get feedback from compiler warning or failures of these configurations, we need to build them. And common practice is to build each configuration separately, independently, and doing a clean build each time. And we know that building a software can take some time. And in this paper, we introduce incremental build of certain configurations, which is building the configurations one after another without cleaning the artifact in between them, and letting the build system reuse the previous artifact to avoid redundant computation for other builds. And for this simple example, we can, for instance, gain 2 seconds with incremental build. And to explore this idea even more, we design an experimental approach for a configuration set of 3 configurations. We incremental build every possible pair of the set. And then we check for the feasibility of incremental build of configurations by checking the build failures. Then we check the efficiency of incremental build by comparing the build time of incremental build and its clean build of the same configurations. Then we check for correctness. We compare the build results of an a configuration incremental build and its clean build. And our criteria are based on the binary size and symbols. And finally, we check for an optimal order, which is the fastest chain of incremental build of configurations that beats all only clean build strategy or even other order of incremental build. And here we can build 3 configurations incrementally in 27 minutes instead of cleanly building them in 45 minutes. We applied our experimental approach to 5 configurable systems. So we generated 20 random configurations, 2 batches of 20 random configurations per system, and these configurations were generated using Feature IDE. And the lessons learned from our experiment is that incremental build of configurations is feasible on the highly configurable system, so 78% for some batches of some systems to 100% of configurations for other systems. The incremental build of a given configuration can outperform its clean build, depending on the configuration built previously, so the ability for the build system to reuse code. And the produced binaries of incremental build are likely to be correct, that's 57%, but it's not always the case. And finally, it is possible to find an optimal ordering that beats all other strategies of incrementally building or clean building them. And for this, we combine incorrect incremental builds, we clean build them, and for the rest, we apply an optimal ordering with these configurations. So to sum up our paper, we introduced the novel problem of incremental build to software configurations. We designed an exploratory study to investigate the benefits and limits of incremental build and quantitative and qualitative analysis of empirical results. And we draw a discussion in the end first for developers, for more experimentation on the incremental build of configurations and find an optimal ordering to accelerate the build of their configurations, instead of just using the incremental build ability of the build system for little changes or through commits between 2 versions. Second, for build system designers to make more expressive build systems that handle incremental build of configurations, avoid and improve the incremental algorithm to manage the configurations. And finally, for researchers to evaluate the incrementality of build system to support variability and automatize a way of automatically finding the optimal ordering of incremental build of configurations instead of testing all of them like we did. So our artifacts are available in the link below, and the artifact is available and reusable. Thank you.
Well, thank you very much. Yeah, Thank you, everyone, for sharing. And our next paper, we have Clement to share with us about his paper, Casualty in Configurable Software Systems. Okay, welcome, Clement. Please go ahead.
Hi. Yeah, thank you very much for the introduction and your interest in our paper Causality in Configurable Software Systems, which is joint work with Crystal Bayer, T-Vise, and Sven Apel. And the context is as here in track, configurable systems. And in fact, almost every practical software system nowadays is configurable, let it be on a compiler level of if-defs, then on a higher variant level on software product lines, but also in daily use in system preferences. And the main challenge here, as we already saw, is the exponentially many configurations that can appear. And fortunately, we have a lot of methods there in the development. For instance, we have feature-oriented software development paradigms. We have SPL testing for testing approaches. In the formal analysis, we build family models to exploit symbolic representations of all these variants and overcome this exponential many configurations problem. But there's a little lack in explanation facilities for such exponentially many configurations. And this is tackled in this paper. Namely, we ask which features or options cause an effect property. And the effect properties can be of various type. It can be functional, non-functional. And here, for instance, in our system configuration setting, we want to have an internet connection config to have a small probability of failure of the connection. And formally, we are inspired by the Harper and Pearl causality. And for that, we assume to have given the set of valid configurations, V, then the set of all configurations which show the effect, for instance, the small probability of failure, and all the other configurations we assume to be non-effects, not showing the effect. And the feature course is then a partial configuration, which means we treat plus features, they're explicitly selected features, and minus features, which are explicitly deselected features. And our definition follows the Harper and Pearl style definition, where we have two conditions. The first one is the sufficiency. We want to have both features selected or explicitly deselected, and the others are not relevant for the course, that are contained in the effect. They all show the effect. And the other thing is the counterfactuality, that if you have the contraposition, if you would drop one condition and the plus or minus features, then you would reach a non-effect, and that's why it might be not a cause of the effect. And our main result is that with a very nice connection to prime implicant computation from circuit optimization, we can compute these feature courses in exponential time and a number of features with a quite nice black box algorithm where we use this prime computation. But still, these features courses can be exponential in the number of features, and we want to explain them, and now we need some kind of methods to also explicate these causal dependencies and these feature courses. And I want to only briefly go into one method we present in the paper. This is responsibility and blame. It's also inspired on such notions of Chokla and Harper when we transfer it to the configurable system setting, and there we quantify the causal impact of such features. And the degree of feature responsibility is defined as for some feature X, some effect instance, we have a value of 1 if it's a full responsible, and 0 if it's this feature is not responsible for the effect. And then we can have given a probability distribution over the effect and define the blame, how to blame this feature for the effect. And one example is, for instance, Simulink aircraft velocity control we consider here, where we have 21 different components here in this aircraft velocity controller. And the configuration of each of these components is whether we introduce redundancy or not to reduce the probability of failure. In fact, this yields to a configurable system with over 2 million variants. And now we can see the effect set as the probability of failure less than, for instance, 2.5%. And we get over 200,000 effects and over 7,000 causes, which is difficult for developers to interpret. And for instance, we can now use our blame approach, which is here for each component, sees how much to blame the feature. And based on that, we can now configure, have a rule of thumb for like causality guided configuration, and see that, okay, the acceleration component and the integrator component have high responsibility for the low probability of failure. That's why they should be introduced with redundancy, and that's why we can have some kind of causality guided configuration of our systems. We did even more. We had a lot of other systems investigated, real-world software systems. We presented logical formula simplification as cause-effect covers as other methods to explicate. And we have also a nice theorem about feature interactions and feature causes as a correspondence, a new method to determine feature interactions. And yeah, the paper is available at arXiv, and it's also the implementation is available, and the artifact is reusable, and you can test it also via GitHub here. Thanks.
Yeah, thank you, Cameron, for the presentation. Yeah, and our next presenter will be Edward. And Edward will present to us about his paper, A Scalable T-Vise Coverage Estimator. Please go ahead.
Yeah, thank you. Hello, everyone. It's my pleasure to be here. So it's a joint work with my colleagues, which is called a Scalable T-Vise Coverage Estimator. And the main idea is the following. When we speak about testing of configurable systems, obviously we cannot test a single configuration, that's not enough, but testing all of them, it's also infeasible. So even with, as was told in the previous presentation, with 20 features, you could have millions of configurations. So what we can do, we can only look at the small subset of configurations. And what in general we want to see is there, we want to see how different features interact with each other, if there is any unexpected interference between them. So what we want to see as many different combinations of features as possible. And one of the most known metrics to measure the coverage of the test suite is T-Vise coverage, that computes how many distinct feature combinations have been covered there. So in particular, we need two numbers. We need to know the number of distinct feature combinations appearing in the test suite of size T, and also we need to know the number of distinct feature combinations that exist in total that satisfy the constraints of the configurable system. And when we try to compute it for large systems, when we have thousands of features, we actually have a problem. For t equal 2, it takes some time. For t equal 3, it's already really hard. For t equal 4, it's basically infeasible. But at the same time, in many cases, we don't really need the precise value of the T-Vise coverage. Some reasonable approximation would be fine in many cases. So our question is, can we design a scalable algorithm to estimate the T-Vise coverage? And the answer of this work is yes. In particular, we provide two algorithms that approximate these two numbers needed to compute the ratio needed to compute this T-Vise coverage. So the first one we call the ProgScope, that estimates the number of distinct feature combinations of size T in a test suite. I don't have time to go into the details of the algorithm, but the idea behind is Monte Carlo tests. And the second algorithm is ApproxMaxCov, where we compute the maximal number of feature combinations. And here we use a different method. We encode the problem into a projected model counting problem. So given a Boolean formula and a subset of variables, we try to see how many assignments that satisfy the formula exist for this subset of variables. And we use an approximate model counter to get the result. For both algorithms, we can guarantee that the result would be probably approximately correct. So given two parameters, epsilon and delta, that you can set up, we can guarantee that the approximation would be within 1 plus minus epsilon factor from the correct value with a probability at least 1 minus delta. We tried our algorithms on a large number of benchmarks. We put 1 hour of time limit, some parameters for epsilon delta. And what we saw that ApproxCov on test suites from 10 to 10,000 variables can complete within a bit more than 10 minutes. However, if we try to compute the exact value, we already have problems to finish within 1 hour for t equal 2. So there were 2 test suites on which we haven't finished. And for t equals 6, only a few of them has been able to finish, and we get a result. With Approxmax the difference is even more drastic. So while for the approximate methods, we can finish on almost everything. So there were only 2 benchmarks that failed to finish within 1 hour for t equals 6. An exact method failed on more than half of the benchmarks for t equal 2. And for t equals 6, it's managed to finish on very small benchmarks where we have 20, 25 features in total. So takeaway, so we propose 2 algorithms that can be used to estimate the T-Vise coverage. They're scalable. We try them out on large benchmarks up to 11,000 of features and T up to 6. We have the guarantees about the approximation of the result, and the implementation is available at GitHub, and also it's it's reusable. Artifact is reusable, and thank you very much.
Yeah. Thank you. Thank you, Edward, for sharing with us. Yeah, there is a question on the chart, and after the presenter all have done, then we will go through the question together. Okay. So our next presenter will be Puya. Sorry, hope I pronounced your name right. The title is On Debugging the Performance of Configurable Software Systems Developer Needs and Tailored to Support. Okay, please go ahead, Puya.
Can you hear me?
Yes, we can hear you.
I'm not sure why I do have issues sharing. It says that fail to publish a screen. Do you know how can I enable that?
Okay. So will you click on that start sharing? Yes. Maybe try again.
But it says that like it shows fail to publish a screen. The screen shouldn't be shared. Do I have permission to share?
Definitely, yeah, definitely. But I would say please try again.
You have to allow Mac OS in your security settings to share the screen, but you don't have to restart your browser, even though it says you do have to do so.
So I should go to security settings and enable what exactly can you show me?
Then you go to privacy, security and privacy, then to privacy.
Yeah, I'm there.
And, screen recording, and then you should take Firefox or Safari or whatever you have.
So I should enable a specific app there in order to add it?
Yes, the app you use here to be here in this room.
Yeah, so basically I use Chrome.
Yeah, then there should be a line with Chrome, and you could have a tick there and allow access.
Yeah, it's already like enabled. I'm confused. It's already Chrome ticked. So let me restart.
Then try it again.
Yeah, that might be the case. I'll rejoin soon.
Well, we'll give it a minute.
It's a really interesting exercise of live causality relationship debugging.
Yeah, yeah. Like the issue exists. I'm not sure why. Chrome is already enabled there. That's so annoying. Maybe I restart the whole computer and join again. Do you have any other like solution beside this? And
So your OS, is it Mac or is it iOS
Yeah,
or is it?
and Chrome is already like enabled in the privacy setting. So I don't see any.
You might choose another browser.
Oh, maybe yeah, I can use Firefox.
Maybe we can answer questions meanwhile, or
Yeah,
it's okay.
sure.
It would be great.
Yeah, maybe we will start with our Clement. There's a question for Clemens. Very nice paper. I wonder if brain is the right word since something your approach is not just traced to problematic features configuration, but perhaps simply to identify relevant parts of configuration. For example, as you say, to establish effect for features, or does responsibility cover the non-brain trace?
Yeah, thank you very much for this question. It's a very good one because actually Harper and Chuckler and Harper, they introduced this term blame, and we don't think that it's really appropriate neither, but it's in the standard in the causality reasoning, and that's why we chose the same term. And in fact, you're right. We identify the relevance or the impact of one feature onto the effect. And the second question is responsibility doesn't cover non-blame traces somehow, because responsibility is always with respect to one context, so with one configuration that shows the effect. And then you have a probability distribution over all the effects, and some kind of averaging over the responsibility then over all these effects. This is the blame. This is the expectation of the responsibility. And that's why it's a little bit a different perspective. The one is the local perspective for each effect instance, and the other one blame is the global perspective on all effects.
Yeah, thanks, Clement. Yeah, I know that the term brain is like introduced in GitHub. Like since GitHub introduced that term brain, it seems like it's widely used in many occasions. Yeah, thank you. Yep, and there's a second question for Aaron. How do you compile the optimal incremental build orders? Is it possible to do it familiar based, or do you use some processings to avoid the blow up?
Okay, so thanks for your question. Basically, what we do is just we build every possible pair, and then we check the minimum time compared to, for configuration, check the minimum time compared to its clean build. Then we take only the correct ones in incremental build, so same binary size and same symbols, and then we use it for the optimal order. And your question on the family pass is quite interesting, but because you can do in one pass, and then you generate each configuration, and you can do based on that. And that's another way of finding it. That's why we say in the discussion to discuss about for researchers, either is it a good point of view to order a set of configurations, or do a family-based approach to generate configurations and explore the configuration space this way. Actually, we have a vision paper that talks about how we can use some commonality on features to explore the configuration space on Friday. So you're welcome if you're interested in it.
Well, thank you, Aaron. And it seems like Priya have got the problem fixed, and let's give Priya 5 minutes to present his paper. Please go ahead.
Do you see my screen now?
Yes.
So do you see the presenter view or presentation is full screen?
I see the full screen.
It's on presenter view on my side.
Is it? So
it is on presenter view. We don't see the full screen, but you see your notes, and here it's better.
Okay, yeah, now it's
Okay, awesome.
Now,
I'm so sorry for the delay. So today I'm talking about Miguel's paper, Miguel's work, basically on debugging the performance of configurable system, developer needs, and tailored tool support. This is a collaboration with Miguel, Nobed, Sven, and Christian. So as you know, this is a session for configurable systems. Most software these days are configurable, and the benefit of configurability is first for users, so they can put together different features in order to build a customized version of the system that they have, but also for developers where they want to use this variability in order to address some specific requirement and build a customized system for their users. And as you know, the most important aspect of software systems, or at least one of the most important aspects, is performance. And when we say performance, we are talking about multiple objectives. This could be execution time of the system, or energy consumption of the system, or operational and maintenance cost. So you're talking about multiple objectives that we or the developer would like to make some trade-off in order to design, implement, or maintain an efficient system, but also from time to time, system face some faults where developer task is to fix these faults for the system. And based on some prior empirical studies, researchers show that like 59% of performance issues, basically of overall faults, are related to configurable related performance issues. And on average, it takes several weeks in order to fix these kind of faults. And also with respect to the patches, 50% of the patches overall is related to performance. But coming up with a specific solution or for deciding each value for the configuration options is not easy task. We know that there are some available solutions for solving this important task. We could use profilers. As you know, many developers and also maintainers use such profiler for the system. We could also search for patches. For example, we could search what part of the code in terms of performance are inefficient and fix them by some prior patterns for fixing those like inefficient code patterns. Also, there are some nice debugging tools out there, either performance-related debugging tools, or we could basically customize non-performance-related debugging and repurpose them for performance, fixing performance issue for the system. But the problem of existing work is that they have mainly focused on measuring or evaluating the accuracy, how good they are, in order to whether predicting what is the performance of the system or optimizing such multi-objective space or making any trade-off in that space. And less work, or possibly this is the first work that focused on measuring or evaluating the usability of performance methods. You could tell how these are used in practice. So in order to understand the landscape, we have done a case study to understand how options and their interaction affect performance, and how in practice these methods are used or information needs are needed in order to design, implement, and maintain such efficient system. So the first case study that we have done focused
Sorry,
on...
Connor, your time is up. Please wrap up your presentation.
Just a wrap-up slide. Thanks. So basically, the focus is identifying the influencing options, what options in the system or in the source code affect performance indicator, what are the option hotspot, where they manifest such issue, and the cause-effect chain. For this purpose, basically, we came up with a solution that is a hybrid approach. We use global and local performance models for identifying the influencing options and also option hotspot, and a hybrid approach by combining CPU profiling and program slicing for identifying the cause-effect chain. Thanks.
Okay, thank you very much. Okay,
Yeah.
now it is our question and answer session. And so Zach have another question for Aaron. How does incremental builds deal with configurations that deal with type depths or other things that might propagate to the large range of artifacts?
So a short answer is that the build system just recompile the artifact and propagate the recompilation, and then you compile the whole project. And and I think a longer answer would be that we should focus more on the kind of nature of the source code changes through configurations, because there are some studies on how are the kind of changes through each commit on the project. But we want to focus on what is the kind of change that applies to a software when we change the configurations, and how are the configurations changing through the versions too. So the answer is it recompiles everything, and we want to detect that or making a better build system. And the second one is there is yet some job to do on this side of combining incremental build and configurations. Thank
you. Yeah, thank you. And any other question? Feel free to type into chat. And I have a quick question for Clemens. So in your test, does the size of the program matters? So if the size of the program does matter, what is the approximate size of the program that you were testing?
Okay, thanks for the question. Actually, we use this as a black box. We use any testing or analysis method, family-based analysis method, to estimate whether the effect is shown in all the configurations or in some effect configurations. And then based on this Boolean somehow information, we can trace down the causes, which means the size doesn't matter. If your analysis method or your testing method copes with the size, with a huge size program, then it can be used also in our method.
I see. Does anyone have anything to add to it?
A question to Sugar C. So a great paper. I really enjoyed it, and I was just thinking about I mean, you go from, because the if devs and so on are enabled through compile time option, and then you bring it to kind of a C native code, and if you can boot you can run the software, does it mean that you brought the compile time option to be like runtime options, and it would be like, is it possible to maybe to configure the subsystem at runtime because you have some C constructs on your software actually? Yeah, and it will look like feature toggles or things like that. I was just wondering.
Yeah, so the code is pretty unoptimal to actually execute, but you can do that. So one of the things we did for evaluation was we did execution equivalence with Sugar C and the original file. And we did that by essentially toggling on the different compile options in real time, like with the code, by specifying them in a file. So you could do that, and that kind of support is there, but you probably wouldn't want to, just because I assume it would be slow. And you're also dealing with a really large file then if you're, working with like a
Yeah, but
real
at least you can just, configure it at runtime instead of building each configuration.
Yeah. The option is there. Thank you.
Oh, we are good.
Yep. Clemens also have a question for Zach, so go ahead.
Yeah. Thank you very much. I like this paper very much as well. I wondered you're some kind of rewriting the names of your variables. Somehow you put this 1, 2, and so on. Do you have also some kind of library database to keep trace of these annotations and then map it back in configurations that you have, for instance, static analysis or code analysis? If you trace an error, then can really reason about your configurations and in desugared code?
Yeah. So all of that information is so when we define the variable, there's nothing like externally that identifies which condition it's associated with. So like back in my example, when I showed like x1, there's nothing that shows x1's associated with the unsigned int flag. However, whenever it's used, then it's wrapped in this if statement, which associates with the condition. And what we're working on right now actually is doing just that. It's taking where these errors appear and then kind of like going up the code to look for these if statements and then associate the conditions with where the error takes place. So it does, but only implicitly.
Okay, you take the trace and then you make a conjunction over all the present conditions and you put out somehow the condition on the configurations. Okay, cool. Thanks.
Oh, thanks. I actually have a question for your paper as well, actually. And it was about dealing with implicit features. And just like, is there any kind of like weighting or challenges that come from how one feature existing might imply that another feature is turned on or off, if that like weighting has any effects?
Yeah. In fact, there are two answers. First, it can be in the valid feature configurations encoded in the feature model, and that's why then if this information is in the feature model, then it's some kind of don't care and not relevant, like presence condition simplification. Also, we drop this information. It's not causally relevant because you're in this world of valid feature configurations. And the other thing is for explication, for explaining the causes, then it becomes again relevant. And then it might be, for instance, that you have this implication would be helpful for the developer, and then you can place it back in the propositional logic formula or in the condition this this implication back to your causes, and then it has a meaning again.
Okay. All right. Great. Thanks.
Yeah. Thank you. And yeah, there's we have a question. Yeah, maybe you can just voice it. Yeah.
Can you? No.
No. Yes, we can hear you now.
Yeah. But have you contrasted your method with non-causality, and what design you have there by the example that you've done?
Yeah, thanks. I did not get it in via voice, but I could read it in the meanwhile. Thank you very much for the question. It's really interesting because actually our evaluation was mainly focused on the on discovering bugs, on discovering the causes, and we did not compare it to a lot of other approaches because usually they really have a white box approach. They do not have the black box approach. They take a look into the code and take a look where is the reason for some bug or whatever, which means it's complementary to our approach where we have a black box approach. We use the analysis method and then we want to estimate the impact of features. But it would be also really nice to estimate whether you could use the data of the analysis results, to what extent you could see the causal information somehow already there with standard methods. In small examples, it's possible to see this also. But for instance, in this redundancy example, you have sizes from formula sizes or causal sizes of 80,000 variables or something like this. It's really difficult. I think we need new methods that then could be compared with our causal methods. But I think there's no big hope to compete with.
Thanks.
Yeah. Any other questions? You can either put your hands up or just like type questions in the chat. Okay. If not, actually, I have a question for Aaron. For parcel integration, like in my concept, when the team is bigger, when our team is bigger, have multiple members, like trying to commit in parallel so that there will be parcel integration happen all over the place. So for me, like there were conflict or there were problem, the number of problems or things happen in direct relationship with number of team members and team size. So in your research, have you considered that are kind of factors?
So the integration of the teams committing on the same project?
Yep.
And you want to incrementally build each addition of the team members?
Yeah, I just wonder, will that be an effect or like affecting like whether the parcel integration work or like is it affecting the results or not? So is the result relevant to team size or that kind of things? Like
no, we are focusing on a fixed version of a software system.
Mm-hmm.
So there are two axes. You have an axis where you commit, and there's the evolution of the software in time, and we fix a given time, which is a version of the software. Then we build the configurations of the same software at these versions. So I think no one would commit at this moment, and it's a fixed version, and we just explored another axis, which is the configuration. So I don't think that it would have an impact on the approach.
I see. Yeah. Thank you. And
thank you.
Thank you. Any other questions? Okay. And there are Puyers mentioned difficulty of such comparison. So beside the sheer size of configuration space, what are the other factors that might contribute to this complexity? And just before Clement answer, this session might end in a few minutes. We will jump to another discussion room, and then so we can still continue. Okay, so please go ahead, Clement. Yeah.
So the question is for Clement. Sorry.
I think that is for Clement. Yeah.
Yeah, thank you very much, Priyan, for this question. Yeah, our approach is very generic. You only use the analysis method, and then you can directly on the analysis results you can apply our method. The difficulty is all in qualitative case. Other methods which are not variability aware or what other analyze highly configurable systems, they could be really specific. And this is how do you compare this with a really highly specific tailored method that is really used to have this reliability of some highly configurable system tailored for that? And if you compare it then with our very generic method, this is some kind of, I wouldn't say unfair, but it would, I think you cannot pears and apples, you cannot compare it too much. And finding another very generic approach which delivers this, I cannot right now imagine, but yeah, maybe then. But I think it's a qualitative complexity which is challenging to answer, because how do you compare these approaches?
Thanks. Yeah.
You're still muted.
Yeah.
Sandy, you're still muted. You're muted the whole
Yep.
time.
Thank you. Yep. Oh, thank you everyone for coming to this, and I hope you have a nice morning, nice afternoon, or nice evening, depending on where you are, and enjoy the conference. And in a minute, we'll be transferred to a separate discussion group. If you would like to stay behind to have further discussion, feel free to do so. Okay. Have fun.